Hello everyone, welcome back to another class. Today's class topic will revolve around polar coordinates. Now, so far we have been dealing with points that are plotted on a Cartesian plane, right? So if I consider a Cartesian plane, I will have my x-axis, I will have my y-axis, and I can identify any point, or I can identify the location of any point on this plane by my x and y coordinates. So this x coordinate describes the horizontal distance with respect to the origin. The y coordinate describes the vertical distance with respect to the origin. And any point that can be described by such coordinates are known as rectangular coordinates, right? If I can describe any point with this ordered pair, then these are known as rectangular coordinates, right? Now, we've only been dealing with Cartesian coordinate systems like this, right? But this is not the only type of coordinate system that we can have. There are many other types of coordinate systems, and for this class, we will look at the polar coordinate system, right? So if I get rid of all of this, so as you can see in this diagram, we have a polar coordinate system, right? This is a polar coordinate system, right? So we can first identify our origin over here, and we can identify the location of each point for polar coordinates with this ordered pair, where we will have r and theta. So this ordered pair identifies the location of any point in my polar coordinate system. So what is r here? R is just going to be the distance between any point. So let's say I consider some point here, right? Let me use a different pen. So if I consider a point here, then the value of r will be the distance from this point all the way to the origin, right? And that will be my value of r. And what will be my theta? Well, theta acts or is defined in the same way as it is defined for a unit circle. Theta will be just my angle from here, from the positive x-axis, rotated anti-clockwise until we reach this point, right? And this will be my angle theta, right? So if I get rid of this, as you can see, we have some point A on this polar coordinate system. So what are the polar coordinates for this point A? Well, as you can see, the distance from the origin to the point A is 3 units, right? So therefore, my value of r will be equal to 3. Why is it 3 units? You can see that this point lies on a circle of radius 3, right? It lies on a circle of radius 3 units whose center is at the origin, right? So my value of r will be equal to 3. And what will be my angle theta? Well, if I rotate from the positive x-axis to this point, you can see that this will be the angle of 30 degrees. So theta will be equal to 30 degrees. So I can describe the coordinates of the point A in polar coordinates to be 3, 30 degrees, right? These will be my polar coordinates. Similarly, I can consider this point B here, right? And you can see that the distance from the point B to the origin is actually going to be 2 units, right? You can see that this point lies on a circle of radius 2 units, right? So my r value for the point B will be 2 units, and you can see that my angle theta, so if I rotate all the way to this point, this will be 240 degrees. So theta will be 240 degrees. So I can describe the polar coordinates for the point B to be 2, 240 degrees, right? Now, the difference between rectangular coordinates and polar coordinates is that unlike rectangular coordinates, we can actually have multiple other coordinates that describe the same location. So for example, if I consider a Cartesian plane, if I consider some point here, then we can say that, let's say this has the coordinate 2, 3, right? This coordinate will be the only coordinate that describes the location of this point. This is a unique coordinate, right? But that is not the case for polar coordinates. So if I consider my point A again, if I consider this point, then we have shown that this has the polar coordinates 3, 30 degrees, right? But that is not the only coordinate that is unique to this point. We can also just add 360 degrees to my angle theta. We can also just subtract 360 degrees from my angle theta, and we will just arrive back at the exact same point, right? If this is 30 degrees, I can just add another 360 degrees and I will come back to this point and we will still have this point, right? So for my point A, we have found that the polar coordinates are 3 and 30 degrees, but we can also have 3, 390 degrees. All we did was add 360 degrees to this. This will also be equivalent to 3, 750 degrees, or we can also consider 3, minus 330 degrees, right? Where we just subtracted 360 from 30. So all of these coordinates describe exactly the same point A. These all describe the same point A, right? And similarly, now not only can we just add 360 degrees or subtract 360 degrees from theta, we can also consider a negative radius, right? We can also consider r to be negative. So how does that work? We found that point A has the coordinates 3, 30 degrees, right? Well, similarly, if I consider negative 3, then I can have the angle 210 degrees, right? So if I rotate from my positive x-axis by 210 degrees, I will be considering this line here in my third quadrant, right? I will arrive at this line. And since I have a negative radius, all I will have to do is go in the opposite direction by 3 units. I will go in the opposite direction by 3 units away from 210 degrees. And I will just arrive at this point, right? So this coordinate also describes the same point. So we can also have a negative radius. Similarly, for the point B, we know that the point B has the coordinates 2, 240 degrees, right? We can once again consider a negative radius. So if I rotate by 60 degrees, so this is 60 degrees, well then I can consider a negative radius of minus 2. So I can have minus 2 and 60 degrees, right? Because if I rotate by 60 degrees and I consider a radius of minus 2, I will just be going from the origin in the opposite direction by 2 units, right? This is 2 units. And I will just arrive at this point B, right? So I can also consider my radius to be negative. And this coordinate describes the same point. So now that we have established how polar coordinate systems work, let's try and consider some rectangular coordinates. So let's say we have a rectangular coordinate such as this, and I want to convert this to polar coordinates. So how can I do this? Well, the very first and easy thing we can do is we can just plot this point on a Cartesian plane. And if I do this, I see that I have my x coordinate to be 0, my y coordinate to be minus 3. So I will have some point here, right? And I can now from this graph easily find my polar coordinates. I see that the distance from this point to my origin is just 3 units. So r will be equal to 3, and I can consider my angle theta to be a rotation all the way anticlockwise to this point, and we know that this will be 270 degrees, right? So my polar coordinates for this point will be 3, 270 degrees. This will be my polar coordinate. Similarly, I can also just rotate clockwise by 90 degrees, right? This is a rotation of 90 degrees clockwise, and I will arrive at this point. So I can also just consider 3 minus 90 degrees, right? This will also describe the exact same point. Or I can also rotate 90 degrees anti-clockwise and consider a negative radius, right? So this will be 90 degrees, and if I consider a negative radius of minus 3, then from the origin I will go in the opposite direction by 3 units. So I can consider minus 3, 90 degrees to describe the exact same point still. So all of these are polar coordinates for this rectangular coordinate. So let's take a look at another point. Let's say we have the point 5, 5. Right? These are rectangular coordinates. I want to convert this into polar coordinates. So once again, I can just easily plot this on a Cartesian plane. So this will be a point somewhere here, 5, 5. So from this, I can just easily construct a right triangle. Right? This length will be 5 units. This length will be 5 units. So how can I find this angle theta? Well, I can just consider the tangent of theta, right? This is equal to y by x, so we will have 5 by 5, which is 1. So I can just consider theta to be equal to the arc tangent of 1, and that will give me 45 degrees. Or I can just remember the fact that if this is 90 degrees, since this length and this length are equal, well, then we have an isosceles triangle. So these remaining angles are going to be equal. So these will both be 45 degrees. These will both be 45 degrees, right? And I can find this length, so the distance from the origin to my point 5, 5, using the Pythagorean theorem, right? We have x squared plus y squared, so we will have 5 squared plus 5 squared. This is equal to root 50. This gives me 5 root 2, right? So my polar coordinates will be 5 root 2, 45 degrees, right? Or I can also consider minus 5 root 2, 225 degrees. So let's consider another point. Let's say we have in rectangular coordinates minus 2, root 3, and minus 6. Once again, I can plot this on my Cartesian plane. So these are both negative, so we're dealing with a point on the third quadrant, right? So we will have a point here, minus 2, root 3, minus 6. And once again, if we construct a right triangle, this is 90 degrees. So this will be minus 6. This point will be minus 2 root 3, right? So once again, I can find this angle theta by considering the tangent of theta. So the opposite, y, will be minus 6 divided by my x, which is minus 2 root 3. So from this, I can find that the value of theta will be equal to 60 degrees. And this is this angle here. This angle inside will be 60 degrees. So we will have to add 180 degrees plus theta to get the actual value of theta for this point in polar coordinates. So we will have 180 degrees plus 60 degrees, which gives us 240 degrees. So this will be our angle. And to find this length, well, I can use the Pythagorean theorem again. So I will have 2 root 3 squared plus 6 squared, and this will give me 4 root 3. So r is equal to 4 root 3. So my polar coordinates for this point will be 4 root 3, 240 degrees. So this will be one of the polar coordinates that represent this rectangular coordinate. Okay, so now that we have learned how to convert rectangular coordinates into polar coordinates, let's do the reverse. Let's consider some polar coordinates and convert them to rectangular coordinates. Let's say we have 8 and 60 degrees. Well, how can I convert this into rectangular coordinates? Well, once again, I can just plot this on a Cartesian plane, right? So I should know that I will have some point that is a distance of 8 units away from the origin, and we have theta given. So this angle here will be 60 degrees. So I can construct this triangle. This will be 90 degrees. If this is 90 and this is 60, the remaining angle will be 30 degrees, right? And from this, I can very easily find my y value and my x value, right? So if I consider sine of 60 degrees, this will be equal to the opposite, y, over the hypotenuse, which is 8. And from this, I can find that y is equal to 8 sine of 60 degrees. This gives me 4 root 3. Similarly, I can consider the cosine of 60 degrees, which gives me x by the hypotenuse 8. And from this, I can find that this is equal to 8 cosine of 60 degrees, which gives me 4. So I have found my x and y coordinates, right? So this will be 4, 4 root 3. And these are my rectangular coordinates for the polar coordinate 8, 60 degrees, right? So let's consider another polar coordinate. Let's say we have 12 minus 3 pi by 3, right? So once again, considering a Cartesian plane, so what is minus 3 pi by 3 equivalent to in degrees? This is equal to minus 120 degrees, right? And since we have a minus sign, we are rotating clockwise. So if I rotate clockwise, so I should have a point in my third quadrant. If I rotate clockwise by 120 degrees, I will have some point here, and this will have the coordinates 12 minus 3 pi by 3 in polar coordinates. And this distance, this length of the hypotenuse will be 12 units. And if I construct a right triangle like this, I can easily find this angle, because if this angle is 120 degrees, then the remaining angle will be 180 degrees minus 120 degrees, right? And that will give me 60 degrees. So this angle here is 60, so that means my remaining angle will be 30 degrees. And from this, I can easily find my x and y coordinates. So once again, if we use some right triangle relationships, I will find that sine of 60 degrees is equal to the opposite over my hypotenuse, which is 12. And we can see that y is equal to 12 times sine of 60 degrees, right? And this gives me 6 root 3, right? So this is going to be this length, but since we're in the third quadrant, our y coordinate should be negative, right? And similarly, I can find the x coordinate to be minus 6. So my x coordinates will be, so my rectangular coordinates will be minus 6 and minus 6 root 3. So this will be my rectangular coordinate. And so I'll give you another problem, and you can try this for yourself. So try and convert this polar coordinate into rectangular coordinates. And if you do so, you should get 4, minus 4. So try and see if you can get this.